Hi, this is Dr. Fred DePiro, and this video is an introduction to OpAmps. Learning objectives include describing the device terminals and its ideal model that involves a dependent source, identifying a feedback configuration versus an open-loop configuration for an OpAmp circuit, analyzing simple OpAmp circuits using the ideal model, and applying the property of a virtual short in order to expedite the analysis. Prereqs are the ability to analyze a circuit using the node voltage method and the use of dependent sources. So what is an OpAmp? Well, it's an amplifier with a high internal gain. When used in combination with a few external components, circuits can be implemented that are really useful and that implement some mathematical operations. That's how it got its name, operational amplifier. Now these operations are on signals, electrical signals, and those most commonly a voltage, and imagine that voltage represents a pressure, a temperature, a position, a velocity, something like that. We can use OpAmps to set up simple circuits that will gain or amplify those signals. We can also create what are called filters in order to pass desired ranges of frequencies of that signal. We can take sums and differences of different signals. We can integrate and differentiate. We can generate waveforms such as sine, triangle, square waves. We can also create a current source, and we can convert the forms of signals, change them around, for example, changing a voltage signal to a current signal, a voltage signal to a frequency signal, and vice versa. Okay, so why use OpAmps to do these kinds of operations? Because other devices like computers, microcontrollers, like an Arduino and so forth, they can do these kinds of math operations too. So why use OpAmps? Well, here's an internal schematic of an OpAmp, 741, a classic device. It contains around 20 transistors or so. Compare that to a computer with millions of transistors. Hence, the operations we can implement using simple OpAmp circuits they're smaller circuits with a lower cost. They can operate faster, hence there's a niche for high-frequency applications. They can also operate with lower power requirements, having far fewer transistors, for example. So in applications in the biomedical area where a device might be embedded in the body and we might want to get a lifetime of, let's say, a year out of a battery, in those kinds of applications, low power is a critical type of requirement. Okay, so how does this thing function? Here's an external perspective of the device, and the voltages that you see are node voltages. Inputs VP and VN appear on the left. Output is over here on the right, V out. You see the power supply connections, plus and minus VS. Okay. And the relationship between the output and these inputs is as follows. It's A times the difference in the node voltages, where A is a large value. Best case you can get out of these currently is around well into the millions, 10 to the 6, 10 to the 8. And you'll realize that if you have a low frequency type of variation in your signals. Okay? More typically, you might have around 10 to the 4. If you have signals that are at some higher frequency with some decent gain applied to them. In any case, we can assume that A is a large value. Okay, so we can model this relationship between inputs and outputs using a dependent source, where the intensity of the dependent source is A times VP minus VN. Now, the inputs on a practical device have a very high input resistance, somewhere between 10 to the 7 and 10 to the 9 ohms. So a very reasonable model for that is just to describe those inputs as an open circuit like this. So the wire just comes in and it's cut off. Okay, it's just a break. So in other words, we're assuming no current coming in at all. This is a very nice arrangement, a nice property to have, because you could think of the op-amp as sensing the voltage at a given node but not drawing any current. That means it's not disturbing the operation of some other circuit whose voltages it's sensing. This is nice. Okay, so 40,000, a million, something like that. Those are big numbers, okay, for the gain. Wow. Well, yes. However, notice also that this output here is limited by the power supply connections, okay? So yes, we have a lot of gain, but that output can only swing between these limits. So therefore, the range of operation, if we think about the difference between VP and VN, that range of operation, when we are getting a linear type of relationship between this voltage difference and the output, that range of operation is very limited. Okay, think microvolts, okay, on that order. Beyond that, the output is in a condition we refer to as saturation. Okay? If this difference between VP and VN gets too big, the output just maxes out at one of the power supply rails, either plus VS, minus VS. We say it's saturated. Okay, now most of the time, for many circuits, we don't allow or don't generally design the circuit so that the output would be saturated. Kind of think of that as an undesirable condition in many cases. Okay? And the way we limit the output voltage is by creating a circuit that employs feedback. Sometimes we also refer to this as closing the loop. It's a connection between the output coming back to the input. So there's some kind of loop involving both the output and the input. Now, in other cases, we do allow the op-amp to saturate, in making use of that maximum gain. These would be referred to as open loop kinds of configurations as opposed to the closed loop configurations. And one example of that is a simple voltage comparator. Suppose you had two voltages coming in and one of them represented the current speed of a device and the other represented a speed limit. Well, if the speed ever got bigger than the speed limit, we could detect that very easily by doing a voltage comparison. As soon as the speed got just slightly larger than the speed limit, the output would swing between one extreme and the other, and we could do something like, shut off the system or raise an alarm, something like that. Okay, so the feedback connection limits gain. Here we see this resistor RF connected between the op-amp's output over here to the VN input. This is a negative feedback type of connection because we made a connection from the output to the negative input. Now, what does this do qualitatively? Well, imagine if VA increases, then forgetting about the rest of the circuit for a moment, but if VA increased, then VN would tend to increase. Okay? Now, if VN increased, we are coming in through the negative input. That means the output would decrease. If the output decreases, then the feedback connection here is going to cause VN to decrease. Okay? Thus, due to the feedback influence, VN is maintained at a small value, as a small value. If the input goes up, the output swings down such that the node voltage of VN remains very nearly constant. Okay, so let's get serious here now. Let's do some analysis and reveal exactly how this feedback effect works and how it's related to these external components. Okay, so we're going to do an analysis of that prior circuit. We're going to use the ideal model that you see here. We're going to assume that the thing is in its linear mode of operation, and in other words, the output is not saturated at the power supply rails. So that's a common assumption, and all we do after we complete the analysis is check and see, is the output actually within those limits, to verify that the given conditions do result in the linear type of operation. Okay, so we'll begin with this relationship. V out is equal to A times Vp minus Vn. Because of the very high input resistance of the device, we'll assume that these currents Ip and In are simply zero. And with those assumptions, we see that the current I2 is going to equal the current I3 because of our assumption that In is 0. Now let's see how this input VA affects the overall output V out. So due to the ideal inputs, I2 equals I3. Using the node voltage technique of analysis, nodal analysis, we can get I2 as VA minus Vn divided by R2. We get I3 as Vn minus V out over Rf, the feedback resistor. So we have that expression here. Also note that Vp is 0. So that means V out, we could simplify that expression a little bit, and we could just say V out is equal to minus A times Vn. Now we have Vn in this expression up here, so let's use the substitution Vn is equal to minus V out over A and simplify the expression that we have. Okay, so here going through those various steps, we'll do our substitution here. You can see V out now appears in this equation, but with a large value of the parameter A, we can simplify that further, and we just and those terms with V out over A drop out, then rearrange, and we get this expression here. V out over VA is equal to minus RF over R2. So you see that overall relationship here between this input and the output of the op-amp. Now, one thing you'll notice right away is that the gain of the overall circuit is determined by the external components RF and R2, not by the op-amp's internal gain parameter. That's a good thing, because the value of A can vary with temperature, age, and manufacturing. You know, each op-amp, even of the same model, won't have the exact same gain. Furthermore, note that we used resistors for these external components, and comparing those against resistors, inductors, and capacitors, resistors are the most stable over time. Okay, they don't change. So thanks to the feedback, and also thanks to our selection of resistors associated with the circuit, the feedback provides us very stable operation. Now, there's this minus sign in here. What's up with that? Well, this basic circuit arrangement is referred to as the inverting configuration. Now, yes, the output does swing negative relative to the input, but first notice, of course, we do have a two-sided supply, in this case plus minus 15 volts, okay, associated with the op-amp, so it's okay that the signal swings negative, the signal at the output. That's all right. Furthermore, as we're building up a larger system with various stages of these op-amps, so long as we have an even number of stages, the negation is eliminated. Now, let's talk for a minute about the range of this signal Vn. Here, the output is limited to that plus minus 15 in this case, yet the gain is very large. That must imply that Vn is very small. in order to have V out be over, extend over this range plus minus 15 and have the very high internal gain, Vn can't be very big at all. So in general, with the feedback, this difference, Vp minus Vn, is tiny. Now, it's so small that we actually refer to the idea of Vp and Vn being virtually shorted. Now, there's no wire directly connecting them, so they're not physically shorted. They're not actually shorted, but due to the action of the feedback, the node voltages Vp and Vn are very nearly identical. So we call this a virtual short. Furthermore, that virtual short can be employed at the start of our analysis as just another one of our assumptions, and that will really expedite the analysis. Now, in this case, because Vp, this connection is grounded, another term you'll run into is the idea that Vn is at virtual ground. So virtual short, virtual ground. Using the idea of the virtual short will hasten analysis. We can illustrate that right here. Starting out with Vn assumed to be at virtual ground, we have I2 equal to I3 due to the high input resistance. Using nodal analysis techniques, now with the virtual ground also, we have Va minus 0 over R2 and 0 minus V out over Rf. Simplifying that, rearranging, and we get the same relationship as before. We didn't have to worry about taking that limit in this case. And this is the way op-amp circuits are generally analyzed using the virtual short concept. Okay. All right, so we talked about the device terminals and its ideal model that involves a dependent source. We talked about identifying a feedback configuration versus an open loop configuration. The feedback configuration will have some element in between the output and the input. We also talked about analyzing simple op-amp circuits using the ideal model. And we talked about the property of a virtual short between the inputs in order to expedite the analysis.